Today we are going to learn about optimizing mixture of experts for scalable AI, focusing on balancing model size with computational efficiency to enhance performance in large-scale deployments.
Welcome to this educational session on optimizing mixture of experts models for scalable AI solutions. Mixture of experts, often abbreviated as MO, is a neural network architecture that divides the task of prediction among multiple expert models, allowing only a subset of these experts to be active for a given input. This design mimics the way teams of specialists tackle complex problems, each expert focusing on a specific aspect of the task. In the context of AI, MO models are becoming increasingly important as they offer a promising solution to the scalability challenges faced by traditional models. By distributing the computational load and activating only a few experts at a time, MO models can maintain high performance levels without overwhelming computational resources. Understanding the structure of MO involves recognizing how these models are organized, typically involving a gating network that decides which experts to activate for a given input. This approach not only enhances efficiency but also makes MO models more adaptable to various tasks, offering a significant advantage over conventional, monolithic AI models.
As AI models continue to grow in complexity, scalability has emerged as a significant challenge. Modern AI systems often require vast amounts of computational power to process high-dimensional data and execute complex tasks. This demand places a strain on available resources, making it difficult to maintain efficiency without sacrificing performance. Scalability in AI refers to the ability of a model to handle increasing amounts of data and computation without a proportional increase in resource usage. One of the primary challenges is balancing the trade-offs between model size and speed. Larger models may offer improved accuracy but often require more computational resources, leading to slower processing times. Conversely, smaller models may be faster but at the cost of reduced accuracy and flexibility. These trade-offs are further complicated by the need to manage high-dimensional data, which can exacerbate the computational load. Scalable AI solutions must address these issues by optimizing resource usage while maintaining or enhancing model performance. Mixture of experts models are particularly well suited to this challenge, as they can dynamically adjust their computational focus based on the task at hand, thereby offering a scalable alternative to traditional AI models. Optimizing computational resources is crucial for the effective deployment of mixture of experts models. One technique is efficient resource allocation, which involves strategically distributing computational tasks to ensure resources are used effectively. In MO models, this can be achieved through parallel processing, where multiple experts operate simultaneously on different aspects of the data. This approach not only speeds up computation but also maximizes the use of available resources. Load balancing is another essential technique, ensuring that no single expert is overwhelmed while others remain underutilized. This balance can be achieved by dynamically adjusting the number of experts activated based on the complexity of the task and the available computational power. Reducing computational overhead is equally important. This can be accomplished by minimizing redundant calculations and optimizing the gating mechanisms that decide which experts to activate. Leveraging cloud-based resources provides additional flexibility and scalability, allowing models to access vast computational power on demand. By integrating these techniques, MO models can operate efficiently, even in resource-constrained environments, without compromising on performance. Balancing model size and performance is a critical consideration in AI development. Larger models typically offer greater precision and the ability to learn complex patterns, but they also require more computational resources. This can lead to increased costs and slower execution times, which are not always feasible, especially in large-scale deployments. To address this, it's essential to find a compromise between model size and performance. One strategy is model pruning, which involves removing redundant or less important parameters from the model without significantly impacting its accuracy. This reduces the overall size of the model, making it more efficient to run while maintaining a high level of performance. Additionally, exploring the trade-offs between precision and computational cost can guide decisions on model architecture. In some cases, a slightly less precise model may be acceptable if it offers significant gains in speed and resource efficiency. Understanding these dynamics allows developers to make informed decisions on the optimal configuration for their specific use case, ensuring that the model remains both effective and efficient. Gating mechanisms are a central component of mixture of experts models, determining which experts are activated for a given input. The gating network effectively decides how to route the input through the model, impacting both efficiency and performance. Designing efficient gating networks requires careful consideration of the model's architecture and the nature of the tasks it will perform. One approach is to use dynamic gating, where the gating decisions are made in real time based on the input data's characteristics. This allows the model to adapt to varying tasks and data distributions, optimizing the use of computational resources. The impact of gating on performance is significant. Effective gating can improve accuracy and efficiency by ensuring that only the most relevant experts are engaged for each task. However, implementing gating mechanisms poses challenges, including the risk of bottlenecks if the gating network becomes a limiting factor. Addressing these challenges involves balancing complexity with efficiency, ensuring that the gating network is both robust and capable of making accurate decisions without introducing excessive computational overhead.
Mixture of experts models have found numerous applications in large-scale AI deployments across various industries. One key benefit of MO in such environments is its ability to handle complex tasks efficiently, making it ideal for applications that require processing large volumes of data or managing diverse data types. For example, in the financial sector, MO models can be used for risk assessment and fraud detection, where the ability to adapt to rapidly changing data patterns is crucial. In the field of natural language processing, MO models enhance language translation and sentiment analysis by leveraging multiple experts to handle different linguistic nuances. Another successful deployment is in the realm of autonomous vehicles, where MO models can process sensor data more efficiently, contributing to real-time decision-making. The scalability advantages of MO models make them particularly appealing for cloud-based services, where they can dynamically allocate resources based on demand. As industries continue to seek ways to optimize their AI systems, the future potential of MO models in sectors such as healthcare, logistics, and entertainment remains promising, offering a scalable solution to meet growing computational demands.
Evaluating the results of optimization in mixture of experts models involves assessing both accuracy and efficiency. Key metrics include accuracy, precision, recall, and computational cost, which together provide a comprehensive view of the model's performance. Balancing these metrics is crucial, as an improvement in one area, such as accuracy, should not come at the expense of efficiency. Tools for performance analysis, such as profiling and benchmarking software, can help identify areas where the model can be further optimized. Interpreting the outcomes of optimization efforts requires a nuanced understanding of the trade-offs involved. For instance, a slight decrease in accuracy may be acceptable if it results in a substantial reduction in computational cost. Continuous improvement strategies involve regularly revisiting the model's configuration, tuning parameters, and experimenting with different optimization techniques. By maintaining a cycle of evaluation and refinement, developers can ensure that their MO models remain competitive and efficient, adapting to new challenges and opportunities as they arise.
The landscape of scalable AI architectures is continuously evolving, driven by both emerging trends and technological advancements. One significant trend is the increasing integration of mixture of experts models with other AI technologies, such as reinforcement learning and generative models. This integration promises to enhance the adaptability and efficiency of AI systems, allowing them to tackle more complex tasks with greater precision. Technological advancements, including improved hardware and cloud computing capabilities, are also playing a crucial role in expanding the scalability of AI models. As MO models become more prevalent, their role in future AI development is expected to grow, offering scalable solutions that can adapt to the diverse needs of various industries. However, this evolution also presents challenges, such as ensuring data privacy and managing the ethical implications of AI deployment. By staying informed about these trends and proactively addressing potential challenges, developers can leverage the opportunities presented by scalable AI architectures, positioning their solutions for success in an increasingly competitive landscape.
In conclusion, optimizing mixture of experts models for scalable AI is a critical endeavor in today's rapidly advancing technological landscape. By employing strategies to balance model size and performance, effectively implementing gating mechanisms, and continuously evaluating optimization results, developers can create AI systems that are both efficient and powerful. Scalability remains a key factor in the success of AI deployments, enabling models to handle increasing demands without compromising on performance. As we look to the future, the potential for MO models in various industries continues to grow, offering exciting opportunities for innovation and advancement. We encourage you to explore these concepts further and apply them to your own AI projects. Thank you for joining us in this session, and we look forward to seeing the impact of your work in the realm of scalable AI solutions.